Hello, all you physics kids out there. Mr. Johansson, and I'm going to go over Enigma on mechanics number 2 with you now. We've done mechanics number 1, but let's go over mechanics number 2 online so we can have that behind us. So if you'll get your copy and look at it, you could print it out, would be handy. But if not, just have it on the computer. So let's start with a quote, shall we? So the quote says from R.L. Stevenson, "Quiet minds cannot be perplexed or frightened, but go on in fortune or misfortune, like the ticking of a clock in a thunderstorm." Something we can all try to be more like. I aspire towards that. I would like to be able to do that, to whether fortune or misfortune, just continue at my pace, at the way I look at the world. We'll try that. Might not be always successful. So we have some homework problems that are there. Maybe we should do them first. Why don't we take a look at that? We can mess with our acceleration formula with that. The first one, says an object falls from rest and is moving at 19.6 meters per second after 2 seconds. What is its acceleration? Now, you might already know this. You could probably figure it out right in your head, but let's do it the proper physics way, because that's what we're learning right now. So we have givens written down, underlined, do it properly. And we have, well, the object is falling from rest. This is what we call a phantom given. It's not explicitly written there, but if it's falling from rest, what's its initial velocity? Right. So VI equals 0 meters over seconds, okay? And it's moving VF at 19.6 meters per second after a time of 2 seconds. So what is its acceleration? Notice I have all my variables lined up, nice and neat, so I could see what formula I would use. This, of course, is extraordinarily simple. What formula am I using? Well, acceleration equals delta V over T. And we know VF minus VI is what delta T is. So now I can do my S and S. All right, my S and S step there is acceleration equals VF minus VI over T. Now we can sub in. VF is 19.6 meters per second minus 0 meters per second. That's all over 2 seconds. When I go ahead and pick up the calculator, you can see I'm going to get 9.8 meters per second per second. The meters per second over seconds, remember that's going to be meters per second times, we invert and multiply, so times 1 over second, so that will give us meters per second squared. Excellent. So the next problem. What is the acceleration of a bullet which starts from rest and is moving at 266 meters per second after 0.09 seconds? Let's try that one. They all go in the same format, which makes it easy. A bullet which starts from rest, again, a phantom given. So we have VI equals 0 meters per second. VF is 266 meters per second after a time of only 0.09 seconds. And again, we're seeking the acceleration. Same thing, right? Formula, acceleration equals delta V over T equals VF minus VI over T. S and S, acceleration equals VF minus VI over T equals 266 meters per second minus 0 meters per second, all over 0.09 seconds. You can see the units are going to work out, which means we almost certainly are doing it correct. And so 266 divided by 0.09, we end up with 2,955.555. Well, which of these numbers can we really talk about? We can assume the 0 is relatively perfect, but the time is 0.09 seconds. That's only one significant figure. So I can't really do all of these numbers. So I can round this to 3,000 meters per second squared, but that still is not being completely honest. I'm still not showing the correct number of significant figures. How can I do that? Well, consider scientific notation. Scientific notation was always advertised as being how to do large or small numbers, but it's really how to do numbers with the correct number of significant figures. So for this, 1, 2, 3. So if I say 3.0, I can say that because it's one more than the amount of significant figures I have. 3.0 times 10 to the third meters per second squared. That would be the best I could say about this answer because I'm showing that I have two significant figures. This, I don't know how many significant figures are significant there. It's really uncertain. So the best I could do was that. If you give me the answer and write it out however you got it, I won't take points off, but I will make fun of you, okay? Because you just can't do that. All right, so if we look at the formula section, we have some more formulas, so we're going to need the next formula there, and that's your VF squared equals VI squared plus 2AD. Just another formula from the reference table. Another way to figure out variables. When you have a different set of variables, you won't be able to use this formula, so what formula can you use? If it's in the reference tables, you know it's legitimate. So I have a section there on units of acceleration. It says acceleration is the change in velocity over a certain time, thus the units are meters per second over second, meters per second for velocity, seconds for time. When you reduce them, they become, well, meters per second squared. All right, it's simply meters per second, or change in velocity over second. We had discussed it as when you are looking at miles per hour per second. You're seeing how your velocity changes every single second, and it's just your change in velocity per second. So this is really just an accounting gimmick coming up with meters per second squared. Not really a big deal. So meters per second squared, that's acceleration, change in velocity over time. The next box is accelerators and cars. All right, now we had talked about having your coffee cup. And if you're in your car and you're driving and you do something to make your coffee cup fling behind you, well, what did you do? What did you do that made what kind of acceleration would make your coffee cup lay over behind you? All right, standing still and suddenly accelerating forward. If you accelerate forward, coffee cup might flip over backward. Can you think of a situation that you could also get your coffee cup to flip over backward, but where you're not having a forward velocity? Think about it. How can you do a forward acceleration without a forward velocity? Maybe some of you are catching on. Sure, you're backing up in your car. You're backing up, maybe backing up pretty fast, and you hit the brakes. When you do that, hit the brakes when you're backing up, and your coffee cup flies backwards. So you were backing up now. Which way were you accelerating? Well, if your coffee cup flew backwards, you must have had a forward acceleration. So if you're backing up and then you hit the brakes, that's a forward acceleration. Because your velocity is that way, your acceleration is that way, you're going to slow down, right? So certainly the accelerator pedal in the car can make this fly
But the brake pedal in the car can make this fly too. So are they both accelerators? You bet they're both accelerators. And your hope is that your brakes are better accelerators than your accelerator pedal. Because while it's reasonable to accelerate rather slowly, sometimes you need to hit the brakes and stop very, very quickly. Hopefully always within the region with which you can stop. We'll see if the next problem does that. But there's given us 3 accelerators in the car. The accelerator, the brake, and what else? What other control device do you have in the car that might enable something, your coffee cup, to go flying? Give you a second. Got it? What else in your car can cause your coffee cup to go flying? Well, how can I get my coffee cup to flip over to the right side? How about if I turn the wheel to the left? That would make the coffee cup flip over to the right. So does that mean the steering wheel is an accelerator? Do I change my direction? If I change my direction, velocity, remember, is both how fast you're going and the direction you're going in. So if I change my direction, I'm changing my velocity. So absolutely, the steering wheel is another accelerator. So you have your brake, your accelerator pedal, and your steering wheel. Your steering wheel will start accelerating you to the right or the left. That's an acceleration. Okay. So let's look at this acceleration sample problem. We have Dirk is riding his motorcycle on a twisty road. He's doing 85 miles an hour, which is 38 meters per second, when he sees a car accident blocking the road ahead of him. What will his acceleration be? What will his acceleration be? All right. Well, let's extract the data. Now tell me, do you always need everything in the problem to write it down? For example, the guy's name is Dirk. Does that show up? Okay, that's being facetious, but not everything is always going to be useful towards solving a problem. So sometimes you'll get things called red herrings, and think about whether you need to even bother with them or not. So his VI is 38 meters per second. What is his VF going to be? It's another phantom given. What's his VF if he's coming to a halt? Well, obviously 0 meters per second. The time, no, I'm sorry, not the time. The distance is 75 meters, and we want to know what his acceleration will be. Now, notice I can't do this the way we've been doing it. I'm going to need a different formula. Well, if you look at the formula right up here, right there, we have VF squared equals VI squared plus 2AD. Will that formula handle it? VI, VF, D, and A? I think that formula will work wonderfully. So, VF squared equals VI squared plus 2AD. All right? So how do I solve that for A? Use your algebra. Now these are 2 separate terms. I got to get it down to 1 separate term if I want to get A by itself. So how about VF squared minus VI squared? All right, I've broken that apart, equals 2AD. How do I get A by itself now? Well, if I divide this side by 2D and divide this side by 2D. I think I've got it. So let me make some room for myself. So S and S, we have A equals VF squared minus VI squared over 2D. You might be able to start seeing the value of rewriting that to keep it all together and keep it clear. So now we substitute in. Well, VF is 0 meters per second. Doesn't matter about squaring that, but I need to square the units anyway. Minus, so that's going to be negative 38
meters per second, and I'm squaring that, dividing that by 2 times that 75 meters. So what do I have there? All right. Well, let's do some calculation. All right. 38. Square it. That's 1,444. That's going to be meters squared per second squared. Right. When we're squaring the units, we're dividing that by, well, 2 times 75 is 150 meters. Now remember, invert and multiply. So times 1 over meters, that meter will cancel that. Am I left with meters per second squared? I am. So you have a sense that this is going to come out the way you would like. And then 1444 divided by 150 equals 9.6 meters per second squared. 9.6 meters per second squared. Can we relate that a little bit to reality? What's your acceleration due to gravity? 9.8 meters per second squared. This is 9.6 meters per second squared. How does that relate to your gravitational acceleration? Well, if I take that and I divide it by my 9.8, I find out what part of a g they call it. Your gravitational acceleration is called a g. This is 0.98 g's. The best motorcycles apparently have a stopping ability of something like 0.8 g's. In other words, you can't really necessarily stop better than exerting 0.9 or 0.8 g's on you. If you try to exceed that, the motorcycle has a tendency to flip over itself. Some people say if you lay the motorcycle down, you can stop faster. Not true. You take longer to stop and you have absolutely no control. So in this situation, our buddy Dirk might not be able to stop in time. So how could Dirk have worked this situation? Perhaps on a backcountry road where you don't have a really long view ahead of you. Going that fast means that you can't stop. By the time you see something that you need to stop for, you just can't stop. So these problems actually work out in real life and give us ideas on how to drive and how to stay safe when we're driving. All right, on the back then we have acceleration and velocity, and I make the same point that I have already made, that in terms of changing your velocity, which is what an acceleration is, if you have your car here and you are having an acceleration in this direction, and you already have a velocity in this direction, some color-coded stuff, hope you like that. What is the result of that? What's the result of that? Well, if you accelerate in the same direction you have your velocity, you're going to end up having an increase in your velocity. You're going to be going faster. All right, how about if you have a car and you have an acceleration and you have your velocity going in the opposite way? What if your velocity is going this way and your acceleration is going that way? What's going to happen to the size of the velocity here? If you are accelerating in the opposite way, well, now your velocity, in green, your velocity is going to become less, right? If you accelerate in the opposite direction,
So your velocity afterwards will be reduced. So we're saying if you hit the brakes, you slow down. If you hit the accelerator pedal, you speed up. And that's basically what we're saying. So if you accelerate in the same direction as your velocity, you are going to be speeding up. Now we see the same thing all the time. If I take this apple and throw it up, on its way up, it had a velocity going this way. Which way was it? Its acceleration. From the time it leaves my hand, it's accelerating down. So on the way up, it's slowing down. On the way down, all right, now its velocity is going this way, the acceleration is going this way. So on the way down, it's speeding up. So this kind of explains all these things you see around you all the time. But we want to quantify them and make them both predictable and calculatable so we can take care of things when we're thinking them through. All right, so that's basically it for mechanics number 2. And we were talking about the coffee cup accelerometer. All right, this coffee cup then we are using regularly in a car to mentally gauge which way we're accelerating. If the coffee cup flings forward, which way are we accelerating? Backward. If the coffee cup flings to the right, which way are we accelerating? To the left. So as an accelerometer, this works beautifully. Do you have an accelerometer on you? Well, yes, you do. Your head is a wonderful accelerometer. If you're going along in a car and you feel your head going that way, you're accelerating the other way. If you're going along in a car and you step on the brakes, you feel your head go forward. One of the more disturbing things I've ever felt was driving along, seeing brake lights way ahead of me on the road and hitting the brake. And my personal accelerometer, my head, didn't move. It felt no change. Even though I was hitting the brakes, I felt nothing like an acceleration. I was hoping that my head would lean forward, meaning that I'm accelerating backwards. In other words, slowing down. I wasn't. Can you think of what was going on? You'll be meeting it soon. It's called black ice. If you're on black ice and you hit the brakes, it's very disturbing to feel you hitting the brakes and you don't feel anything. You are continuing to move along unchanged. Very disturbing. So that's when your driving skills are really put to the test. I was able to stop by getting over onto the side of the road where I could get some friction with something and gently hitting the brakes. I stopped about 10, 15 feet before I hit the car ahead of me. Black ice, very unforgiving. So good to be thinking about these accelerations. Thanks for watching.